Neurons communicate with each other through their dendrites and axon. Generally, incoming signals are received at dendrites, while outgoing signals travel along the axon to the nerve terminal. In order to achieve rapid communication over its long axon, the neuron sends electrical signals, known as nerve impulses, or action potentials, from the cell body to the nerve terminal. An action potential is essentially a brief reversal of electric polarity of the cell membrane. Cells are polarized, meaning there is an electrical voltage across the cell membrane. In a resting neuron, the typical voltage, known as the resting membrane potential, is about -70 millivolts. The negative value means the cell is more negative on the inside. At this resting state, there are concentration gradients of sodium and potassium across the membrane. More sodium outside the cell and more potassium inside the cell. These gradients are maintained by the sodium-potassium pump, which constantly brings potassium in and pumps sodium out of the cell. A neuron is typically stimulated at the dendrites and the signals spread through the soma. Excitatory signals at dendrites open ligand-gated sodium channels and allow sodium to flow into the cell. This neutralizes some of the negative charge inside the cell and makes the membrane voltage less negative. This is known as depolarization as the cell membrane becomes less polarized. The influx of sodium diffuses inside the neuron and produces a current that travels toward the axon hillock. If the summation of all input signals is excitatory and is strong enough when it reaches the axon hillock, an action potential is generated and travels down the axon to the nerve terminal. The axon hillock is known as the cell's trigger zone, as this is where action potentials usually start. This is because action potentials are produced by voltage-gated ion channels that are most concentrated at the axon hillock. Voltage-gated ion channels are passageways for ions in and out of the cell, and as their names suggest, are regulated by membrane voltage. They open at some values of the membrane potential and close at others. For an action potential to be generated, the signal must be strong enough to bring the membrane voltage to a critical value called the threshold, typically about -55 millivolts. This is the minimum required to open voltage-gated ion channels. At threshold, sodium channels open quickly. Potassium channels also open, but do so more slowly. The initial effect is therefore due to sodium influx. As sodium ions rush into the cell, the inside of the cell becomes more positive, and this further depolarizes the cell membrane. The increasing voltage in turn causes even more sodium channels to open. This positive feedback continues until all sodium channels are open, and corresponds to the rising phase of action potential. Note that the polarity across the cell membrane is now reversed. As the action potential nears its peak, sodium channels begin to close. By this time, the slow potassium channels are fully open. Potassium ions rush out of the cell, and the voltage quickly returns to its original resting value. This is the falling phase. Note that sodium and potassium have now switched places across the membrane. As the potassium gates are also slow to close, potassium continues to leave the cell a little longer, resulting in a negative overshoot called hyperpolarization. The resting membrane potential is then slowly restored, thanks to diffusion and the sodium-potassium pump. During and shortly after an action potential is generated, it is impossible or very difficult to stimulate that part of the membrane to fire again. This is known as the refractory period, which consists of absolute refractory and relative refractory. The absolute refractory period lasts from the start of an action potential to the point the voltage first returns to the resting membrane value. During this time, sodium channels are open and subsequently inactivated while closing and thus unable to respond to new stimulations. The relative refractory period lasts until the end of hyperpolarization. During this time, some potassium channels are still open, making it difficult for the membrane to depolarize, and a much stronger signal is required to induce a new response. During an action potential, the sodium influx, which occurred at one point on the axon, spreads along the membrane, depolarizing the adjacent patch, generating another action potential. The sodium currents diffuse in both directions, but the refractory properties of ion channels ensure that action potential propagates only in one direction. This is because only the unfired patch of the axon can respond with an action potential. The part that has just fired is unresponsive until the action potential is safely out of range. An action potential generated at the axon hillock usually travels down the axon to the nerve terminal and not back to the cell body. This is because the axon has more voltage-gated ion channels than the cell body.
Quiz time.
Are you a fan of Alila Medical videos? If so, you will love our new Alila Academy. Based entirely on our highly effective animated mini lectures, our courses are designed to follow a typical syllabus in each subject. Each topic is extensively illustrated and comes with quizzes to test your understanding, downloadable PDFs for a quick review, as well as images for you to use in school projects or presentations. We are known for producing highly effective animated videos that explain the most difficult concepts in record time. We have no doubt that our courses will be a lifesaver for both students and teachers alike, so do come check them out. Alila Academy. Clear, concise, effective, with extensive visual resource. No one explains like Alila does.